Hi, Sam here from Roberts Geospatial. Welcome to part 4 of our Coorabulka vegetation study. In this part we're going to build the product processing pipeline to compute our vegetation index. So I'll go back to, we'll go to the demo Coorabulka product database that we built earlier. And down here we created a collated mosaic sequence. So let's work with that. I can close that now. So we have a collated mosaic sequence. We look at the preview. Here's our natural color rendering of our spectral data. So at this point in time we have a virtual raster that has all the fields and bands in it from the original scene assembly virtual raster. And it also has multiple time points that we've created by building multiple mosaics and combining them together into a sequence. So now we're going to start building a processing chain, or there are other ways to describe it. You can describe it as a cascade or as a waterfall. The way to understand it is that processing will proceed from the top of this tree down through the branches right out to the leaves. So if you change anything in this tree, everything that is subordinate to that processing operation will get updated. So firstly, I'll right click and we'll start by just creating a rendering algorithm which will store in the product. And this is a convenience. It means we don't have to give it a file name, and it's stored with the product database, and we always know where we can find it. So let's just say natural color with atmospheric removal with pan sharpening. Remember, we're working with a collated mosaic, so we don't need any masking now. So I've got a rendering algorithm there. I can open that in ProRaster and that will display. That's fine. So if I come to the algorithm property page, you can see here the coordinate system is UTM. So it's a projected coordinate system. In other words, the system has decided that the coordinate systems for the scenes are compatible, and it's kept that scene coordinate system. Hasn't changed it to any kind of global geodetic coordinate system, geographic coordinate system. So we've got a good coordinate system to work with for processing. So we're going to stick with that. That means we won't need to do any reprojection. So right clicking on this, here's our reproject option. We're not going to need to do that. Up here we have mask by raster. We've already masked, so we're not going to need to do any masking. So we can go straight to computing our vegetation index. So I'll add that in as a new operation. So here's our spectral index product operation property page, and we need to fill out all of the things in this page. So in the product editor, the input raster will be some virtual raster. It will come from the parent product, the parent operation, and the output raster will be a virtual raster, and it will be the child operation. Now in both cases the system fills in this data for you automatically. So our input is the collated mosaic sequence. Our output is going to be index a.mvr, and you can see that if I click on this button I can't change the destination and I can't change the source. That's all fixed. So coming up here to our spectral target, remember that our input is derived from our scene assembly virtual raster, and we're looking at Landsat level 1 data. So the data that's supplied to you are digital numbers, and they've been retained in the virtual raster, so they're available here as a spectral target. But in that virtual raster we also corrected those digital numbers to compute top of atmosphere radiance. So that's a step further down the processing pipeline. And we also computed in that same virtual raster top of atmosphere reflectance. So all of these three spectral targets are available for you to compute your index from. So which should you use? Well, ProRaster will always select the most advanced spectral target by default. So in other words, the spectral target that is furthest down the processing chain. And that's what I would recommend. So I'm going to choose top of atmosphere reflectance. The other reason to choose reflectance over something like digital numbers is that reflectance has been scaled to values between roughly between 0 and 1. There may be values below 0 or above 1, but it's roughly between 0 and 1. And a lot of the spectral index formulas will actually assume that your data is reflectance and that it's between 0 and 1. So if you want to get a valid result from your formula, you may have to have it scaled. There are other formulas that don't require that, but some of them do. So we're going to choose top of atmosphere reflectance. We're going to output calculations for each source event. So this is saying we have a sequence. Each event in the sequence is a time point, and we're going to compute calculations for each event. That will be ticked on by default. You probably will never change that. We have the option to scale the data, and all that will do is divide the input data by this value, whatever you type in here, the scaling factor. We don't need to scale this data because it's already reflectance and it's already scaled. But if we use digital numbers, then you might decide to scale that data. You can also harmonize the data. It says here it clamps the input values to between 0 and 1. So this is not a clip, it's a clamp. That means that anything that's below 0 will become 0, and anything that's above 1 will become 1. So the data doesn't get thrown away, it just gets sucked in between that range 0 to 1. So we won't need to do that for our vegetation index. So that's just setting up the input, and then down here we have the output. So we have all these different categories, and in these categories you'll find individual spectral indexes that are available to you. Now the ones that will be presented in this list are the ones for which you have appropriate spectral bands in your source raster. So if the spectral index requires a thermal band and you're using Sentinel-2 data and it doesn't have a thermal band, well then any index that requires that thermal band won't be displayed in this list. So the ones that are in this list are only those ones that the system knows that you can compute. So if you click on them, you'll see down here it tells you the name of the index, and then down here it will tell you the formula that's used to compute that index. So for this one, for example, we have SWIR2 divided by near plus green divided by red. So these variables, green, red, near, SWIR2, these variables refer to different spectral bands. And if you look in the ProRaster user guide documentation, which is on Robert's Geospatial website, you'll find a list of all of these variable names and what they refer to. So for different satellite constellations or different families, these things are, so when we import the data, we define for each band that we input what its spectral code is, and that's remembered throughout the processing system so that we can always find those bands in the virtual rasters and target them appropriately. So you can tick all these things on, as many as you want. There are absolutely squillions of them. Here are soil indexes, fire indexes. So here, for example, is normalized burn ratio. That's a fairly common one. But for this study, we're going to go into vegetation. Now you can see that there are a squillion different vegetation indexes. As many as we use in this study NDVI, which is the Normalised Difference Vegetation Index. This is very widely used. It has a scientific basis behind it, which is very solid, and so it's a very standard index for vegetation analysis. And here we have near infrared minus the red divided by the near infrared plus the red. So I'm just going to choose that one index and hit OK, and we have a new operation in our processing pipeline. We can preview this now, and here it is. So we've gone from, our preview has changed from a red, green, blue rendering of spectral data using natural color. Now we've only got one field, one band in our raster. So everything's disappeared. We now only have one band, and that's NDVI. So when we render it, we just get this pseudo color display, red to blue, and or blue to red, sorry, and that shows you the vegetation index. So when I render this thing, everything is being computed in real time. So we're going right back to the original TIFF files. We're bringing that TIFF data from those individual bands. We're correcting them to top of atmosphere. That's bringing in another raster for the solar azimuth, and so there's a per pixel solar correction going on to create top of atmosphere. That's going into your scene assembly virtual raster. Then we have a second virtual raster working on that to create the spectral index, and that's what we're actually rendering here. And as we zoom in, the computer will be working in the background to evaluate the value at all of these pixels, going right back to those original TIFF files and drawing data through the processing pipeline. So that's our spectral index. So what we do now is focus down on the study area that we're actually interested in, which is the station. So we need to clip to a polygon. So add a clip to polygon operation. Again, our input and our output are defined for us by the system. And then we need to browse to a polygon. This has to be in a map info table format, and if you've used it before, it will come into this drop down list. So I have one here, Coorabulka Queensland polygon, which I acquired from a Queensland government website, and I think I mentioned before that I don't think it's quite valid, but not to worry. Okay, so we're now clipping that same data to that polygon, and again the clipping all happens in real time. So now we just have the data that's inside the Coorabulka Station boundary. Okay, so now that we have our clipped vegetation index, let's go and compute some statistics. So right click, and down here we have statistics. Input and output as per usual are fixed. We can process a field and all of the bands, and you can select the field, or you can process just a field and an individual band. In this case we've only got one field and one band, so we'll process everything. Compute statistics for each individual event. This will be ticked on by default. Oops, don't tick it off, because we want to get individual statistics for each event in our sequence, each time point. And then we have the resolution level. And this is something you can adjust up and down, and this refers to the resolution level in the raster. So resolution level 0 is the base resolution, and with Landsat data that will be the natural resolution of the Landsat data, which is 30 meter cell size. Each cell is 30 by 30. If you go up the pyramid to resolution level 1, 2, 3, well then the cell size doubles each time you go up. So if I go up to resolution level 1, I'm looking at 60 meter cells, 2, 120 meter cells, 3, 240 meter cells. So I'm going up the pyramid, and my statistics calculation will get faster because I'll be effectively looking at less data. At the same time, if you go down to -1, your cell size is halving, so it's 15 meters. Now it's 7.5 meters. And in order to get down to that cell size, which is smaller than the natural resolution, it's going to then employ some kind of interpolation. Might be bicubic interpolation, for example. And it's probably unusual that you would do that. So let's just go for the natural resolution level 30 meters, which is resolution level 0. Hit OK. Now, at this point, your computer is going to actually do some real work. And it's going to go and draw all that data through your processing pipeline, right from the original TIFF files that were supplied in the scene, and it's going to compute all the statistics and evaluate all those virtual rasters that are in that chain. So for a large data set, that will take a little while. So here we have our statistics computed. So let's take a look at it. In this case, we have 4 events. In the final study, we'll have 49 events, but in this example, we've got 4 events. You can select an event from this drop list, and as you can see, the statistics change when you do that, or you can cycle through them with these little buttons. There are a couple of buttons here on the summary page. View the statistics report in your default text editor. So you'll see that this thing produces a report, and here are the file names. On the operation page in your XML, your report file name is statsa.txt. There's a statsa.sttx, that's a binary file that the system uses to store the statistics. You won't use that directly. And then there's a statsa.csv, which contains some of the statistics in a comma delimited format. So when I open the report in a text file, you can see that you get readable data in this report, and it goes on and on and on and on and on, and it includes all this data from the histogram computations, so that may be important to you. Going back to that summary page, we can also click on this button, view the statistics in your default spreadsheet editor. So now it's going to open the CSV file, and that will come up in Excel in my case, and you get all these different columns with all the various data in it. Here's the variance, the maximum, the mean, and so it goes on. So there are a number of property pages here for statistics. These are our sample counts. So the one we're mainly interested in is the number of valid samples. So these valid samples actually contain valid data. Each sample is a cell in your raster. We know that the cells are 30 by 30 meters because this is Landsat data, and so we know that we have this many valid samples times by 30 by 30, that's our area. The minimum value, the maximum value, so these are our summary statistics, the mean value, variance, standard deviation, signal to noise ratio, and then we also compute a histogram distribution, and from that we draw some quartiles. So this is the lower quartile, this is the value at which the value at which 25% of the data is below this value and 75% is above the value. The upper quartile is the value where 75% of the data is below it and 25% is above. This is the interquartile range, which is the range between those two values. The median is effectively the 50% quartile. That's the data value that's right in the middle of the distribution. So there's 50% of the data values are less than the median, and 50% of the data values are more than the median. And you have the mode. The mode is the most common value, so the value that most commonly occurs in the data set. So when we look at the histogram, the mode will be at that peak of that histogram. And then we have a skewness value. Skewness of 1 means that you have a normal histogram distribution. If it's greater than 1, then the distribution is skewed to higher values. If it's less than 1, the distribution is skewed to lower values. On the spatial page, it tells you your cell size, so that's critical information for working out the area of the thing that you're looking at. So then if you multiply the number of valid cells by the cell size, then you get this area, in this case in meters squared. And we have some spatial cell-to-cell statistics. They're something you probably won't look at very often. I won't explain them. And then we have this little report option, which allows you to type in a value. So if I put in, say, 0.15, hit return, then it says, and by ticking value, I've indicated that I've put in an actual data value rather than a percentage. And that value is, I can tick here either above or below. So it says that 42.79% of the data is equal to or higher than the value of 0.15. If I hit below, then it says 57.2% of the data is less than the value 0.15. And this corresponds to all these cells or an area of this. If I change this to percentage and I say 25%, which I put in as 0.25, so 25% of the data is less than the value 0.126. So it's giving me the value at 25% of the data. If I go back to the summary page, you'll find that that's the lower quartile, 0.126. And you can put in any value here and evaluate that expression. And then we have the histogram page. So here's our histogram distribution. Here the data values along the bottom, and along here we have our count or frequency. And you can see that these histograms are skewed off to the right. I think this primary peak represents the desert country, where there's very little vegetation, sparse vegetation. The vegetation is probably of very little value for grazing. But then out to the right hand side of the distribution is actual vegetation that is of value to the grazier. So it's this area that we're going to be looking at in more detail later on. Now you can see this as a spreadsheet, and there's the values that we saw before from the report, all reflected in that spreadsheet, or as a graph, and you can put a bit of stretch onto the vertical axis of this graph in order to see more detail in this data if you want. There's a bit too much stretch. So bearing in mind that we're interested in that data that is to the right of the primary histogram peak, let's put in a calculator operation to clip out the data that's below that area and focus in on the data that we're really interested in. So let's go back to our spectral index and let's go calculator. So it brings up the raster calculator. There's only one variable as input, that's A00, and that's our NDVI. It's telling you that it's come from index A, which is the raster, the vegetation field, and the band name is NDVI. Our output is fixed. So I'm going to do a clip operation, so clip, or perhaps we'll just do well, I'll show you two ways to do it. So let's do an if then else statement. So we do condition. So if A00, which is the NDVI variable, is greater than or equal to 0.15, that's going to be my cutoff, then output A00. Otherwise, output null. So that's doing a clip manually using an if then else statement. So let's hit OK. Now we have our calculator expression in here, and if we look at the preview, we've clipped out all of these low values. Now let's add our clip by polygon back into there. And look at our preview again. So now we're clipping down to just the Coorabulka Station. And you can see that we've reduced that. Let's compute statistics again. It's all good. And just one point, you'll notice that I always put the clip to polygon as the last operation before I compute statistics. Now, as a general rule, it doesn't matter what order you put the operations, it makes no difference, except for the fact that when you compute statistics immediately after a clip to polygon operation, you get some additional information in the statistics about what cells were inside the polygon but valid or invalid, which you will otherwise lose from other operations. So there is an advantage to putting your clip to polygon as the very last item in your operation tree before you compute statistics. So if we look at the histogram now, you can see here was our peak. We've chopped off most of it, and now we've only got the data that is above 0.15. So just one final little demo here. So if I was to go into this calculator operation and edit it, so let's I change that cutoff value to 2.20, for example. When I hit OK, it's going to, by default, it will update this calculator operation, and then it will run all of the operations that are subordinate to it. So you'll see that as soon as I do that, it will start computing statistics. So it's recomputing these statistics for the calculator operation, now set to 0.2. So let's just let it complete that. It will only take a few seconds longer than hoped. Here it comes. The old Skull Canyon's working. And go into those statistics now and look at the histogram, and you can see that we've cut off that peak that represented the desert area. Now we're only looking above 0.2. If I was to come right up here to the top and edit the sequence itself, let's say I was to add in another collated mosaic or delete one or whatever, then it would recompute everything. So, and I can simulate that just by saying execute operation. And now it's rebuilding everything that you can see in the tree. So it's recomputing statistics here for the spectral index. And then once that's done, it's going to go down into the calculator and recompute the statistics here for the clipped spectral index. Now, for this particular product, we've only got a few time points, and so it doesn't take very long. But in the actual product that I generated for this data set, there are 49 time points, and computing those statistics takes a few minutes for each one, and you might have multiple statistics calculations. So that's where you want to start taking control of your execution and perhaps putting it on pause by hitting this and controlling it manually using execute operation.